you're having difficulty understanding intermolecular forces, you are not alone. It is one of those concepts in chemistry that, quite frankly, is as clear as mud. It isn't easy. It's so slightly confusing. What I'm going to suggest that you do is listen to what I have to say. Try to not be distracted by anything else around you. Don't worry about looking at any screen. Just think about what I'm saying, and hopefully I can go ahead and explain it to you so that you can understand it and then use it in your chemistry studies. Intermolecular forces are the forces between molecules. Now, remember what molecules are. Molecules are non-metal atoms bonding to other non-metal atoms in covalent bonds. And these clusters of atoms that we call molecules have two types of bonds. The polar covalent bond, where the sharing of the electrons between the atoms is unequal, and non-polar covalent bonds, where the sharing of the two electrons we say is equal or fairly equal. The bonding inside of a molecule sets up whether the molecule, we call it polar or non-polar. And again, the labels polar and non-polar have to do with where the electrons that are constantly flying around, where they normally can be found. Are they evenly distributed throughout the molecule, or are some electrons typically on one end than another? And if that's the case, then if you have more electrons on one end, you have a negative end to the molecule, and the absence of electrons somewhere else on the molecule makes it a positive end, right? Because you have your nucleus, which has protons and neutrons. The intermolecular force that's always between molecules, doesn't matter if there's polar bonds, is what's called London dispersion forces. In other words, electrons are constantly flying around, and that at any moment you could have more electrons on one end of the molecule than another, which sets up this temporary separation of charge, which actually might induce other molecules around it, depending on how close they are, to do the same. London dispersion forces typically are taught as, in high school chemistry in New York, I can tell you, as just weak attractions, sometimes just called van der Waals forces. The labeling is partly what makes everything so hard sometimes to understand, and it's unclear. But all molecules, whether or not they're polar or non-polar, have London dispersion forces. Van der Waals forces are actually just the intermolecular forces between molecules, no matter what kind. All right, that's the true label. In New York State, for the Regents chemistry exam years ago, we used to use the label Van der Waals forces for those weak attractions, and the labeling, again, somewhere along the line, it kind of got twisted. So just double check with your notes and your teacher and your professor, or when you're going to take a test, as to the labeling. But London dispersion forces are these temporary dipoles that get set up just when electrons are on one end versus another, and that happens with all molecules. Now, if you have a nonpolar molecule, meaning that you look at the molecule and the electrons are evenly distributed throughout the entire molecule, you only have London dispersion forces. If you have polar molecules, then you also have what's known as dipole-dipole forces, because the arrangement, the bonding and then the arrangement of those bonds in a molecule are set up that you always have electrons concentrated on one end than another. That sets up a polar molecule. Polar to polar molecule attraction is a dipole-dipole force. Now, where it gets as clear as mud is that sometimes the London dispersion forces for a molecule can be stronger than the dipole-dipole forces for a polar molecule. What you're going to have to do is you let the data in the question lead you to the explanation. In other words, if you're comparing two different compounds and one compound has a higher boiling point than the other, but you look at the formula and you know it's a nonpolar molecule, the way you would explain it is say, hey, the London dispersion forces here are stronger than the dipole-dipole and London dispersion forces for the other molecule. So let the data lead you for your explanation. The other thing with London dispersion forces is that they are stronger between molecules that are larger. It has nothing to do with mass, so don't use mass as part of your explanation. It has to do with the size of the atoms in the molecule, because the bigger the atom, the more electrons. The more electrons and the more space that the electrons have to be constantly moving around in, the easier it is for it to set up this temporary dipole. The more polarizable it is, which is another term that's used. But these terms make sure you understand, right, that it has to do with electrons all of a sudden being concentrated more on one end than another. And it could just be, one more over on one side and one less on the other. Other than London dispersion forces and then your dipole-dipole attractions, which are your polar molecule attractions, is hydrogen bonding. And just by the label, it makes it confusing. So my suggestion would be to put the word attraction after hydrogen bonding. So hydrogen bonding attractions. Hydrogen bonding attractions occur for molecules that contain oxygen, nitrogen, or fluorine bonded to hydrogen. Hydrogen, of course, is the smallest atom we have, 1 proton, 1 electron. When hydrogen is sharing its electron with an electron from those 3 very electronegative elements, the pull of the electron pair in the bond is obviously closer to the higher electronegative element, and it sets up a very big separation of charge. Plus hydrogen now, if the 1 electron is closer to the other atom in the bond, leaves just a proton, a positive charge. These are your very strong, super duper, as I call them in class, dipole-dipole attractions. Water, H2O, ammonia, NH3, and hydrogen fluoride, HF, all have hydrogen bonding attractions. But if you have bigger molecules that contain oxygen and hydrogen bonds or nitrogen and hydrogen bonds, they also can have hydrogen bonding attractions. And again, it sets up the properties for the different compounds that contain these types of bonds. For example, water boils at 100 degrees Celsius. That's extremely high. And if you compare it, H2O to H2S or H2SE or H2TE, I'm just going down that column on the periodic table, the boiling points for those other compounds is much lower because the attractions between the molecules is weaker. I hope this helps. I'm going to give you one classic cheesy analogy that I came up with to help explain this, and that has to do with you and your friendships. You know how you have some friends that kind of come and go, and it's not really a strong friendship. You might even call it an acquaintance. They kind of come and go in your life. Maybe right now, whether you're in high school or college, if you're taking chem, you might have, a lab partner, so you kind of strike up a friendship, but you only meet, during class or whatever, or, you work with somebody, but you kind of chit-chat with them at work, but you don't really hang out with them. I kind of call that the analogy of London dispersion forces, right? That they're kind of in your life, but they're in and out of your life. It's kind of like setting up those temporary dipoles. Then you have maybe a group of friends, maybe 5 to 10 friends that you hang out with from time to time, are pretty steady. Maybe every weekend you go to a movie, you go bowling, you hang out, you go to dinner or whatever it is. And with those friends, it's fairly constant. Sometimes, maybe you hang out or chit-chat more with one of the friends in the group that night versus another weekend or whatever. And that's more like your dipole. That's pretty steady. And then, of course, typically when you have your BFF, which we didn't use the lingo back in the day, but, you're very good friends, your trusted friends, the friend that, you trust when you have to really talk to somebody and get their advice, or, you're just really good friends. You've been through everything together. That's more like your hydrogen bonding attraction, that no matter what, they're there for you and you're there for them. So just like your interactions with people, sometimes they're weak, sometimes they're strong, but you're always interacting, hence London dispersion forces, right? You can kind of just keep that in the back of your mind and help you find your way here with the good old mud, the clear as mud for intermolecular forces.